Zoom Helms doing that? There we go. Perfect.
Cool.
All right, go for it, Jack.
Yeah, good evening, everybody. Thanks for coming to the meeting in whatever manner you attended. This is Jack, KK6YWG. Just wanted to have a quick club announcement for club members. We're looking to do some maintenance out at the Clark Valley repeater site. We have a lot of work that needs to be done before the end of the school year in order to kind of finalize some of the Arden stuff. So if you're interested in mesh networking or learning how to, take a big dish down from a piece of pipe, very salivating things. So if you're interested, you can contact me via direct on the usual channels, or get in touch with our projects manager, KM6IA. That's it. That's all I got. Thanks.
I guess the one other thing is that I think David is going to post it out soon, but we're looking into positions for next academic year. So all you people out there who are interested in, I guess, helping out the club in some shape or form, I think David is going to have that out in a day or two. So keep an eye out for that. And without further ado, our presenter, I'll let you take it away, Mark.
Good evening, Cal Poly. I'm Mark Schaefer, WB6CIA, as was given to me by the FCC back in 1968. And I've kept the call ever since, didn't bother to change it at all. I'm a Cal Poly graduate, except it's the other guys, Cal Poly Pomona, back in 1979. And I spent 35 years now at Jet Propulsion Laboratory and 7 years with SpaceX. And and I've kept my ham license throughout. And just last night, probably about 11 hours ago, I talked to the Astral Islands just south of French Polynesia, TX5N, very heavy into operating, and I worked him on 40 CW. He was also on, I worked him on 10 meters and 15 meters. So I'd like to get him on 80, but we'll see. And this is a picture of me by my son, Alexander. He gave that to me for my birthday. So he's older than you guys now by a couple of years. So like I said, I started in Bellflower in 1968, got my ham license. And back in those days, a novice had 75 watts, crystal controlled, and you had a separate transmitter and receiver. So all you could do was transmit on a crystal frequency and then tune up and down for somebody who had a crystal close by your frequency that could that you could pick up and talk to each other with 75 watts. Had a dipole, and that was lots of fun. And back in '68, the sunspots were tremendous, getting above 200. So propagation was very good, especially on 15 meters. But I worked a lot of stuff on 40 meters too. And took me 6 months to get my general. And then that was back when you had to do 13 words per minute and go to the FCC in downtown LA. And they gave you a receiving test, and you had to pass that before they give you a sending test, and you had to pass that. And then you got the written test with 50 questions. So let's see, I was 12 when I got my general, 14 at advanced, and 15 as extra. And So I've just been renewing that ever since. And we've been having quite a dry spell, and I haven't been on the air that much the past few years, especially when I was working at SpaceX. You know, it was like they didn't care what time you came in the during the day, just as long as you put in your 24 hours a day. So that was a lot of work, but it was worth it. Anyway, so I went to Cal Poly Pomona and did a slow scan television converter for my senior project, which I would recommend looking at your peripheral equipment, because in order to build a slow scan converter, I also had to generate a slow scan television signal and a video signal. So I had to have a videotape recorder, a NTSC camera, and a slow scan television monitor, and I had to have that along with the regular test equipment like oscilloscope and DVMs and such, and power supplies, just to get the senior project going. So plus I was working at halftime at home and then halftime at the senior project lab in Pomona, a 25-mile drive between. And half the time I was repairing the traveling damage. So try and come up with a senior project that you don't need a lot of extra peripheral equipment in order to get it going. But I did graduate, and it was just a very good time to graduate in March of 1979, because that was also the month people were interviewing, and I interviewed with the Jet Propulsion Laboratory. They actually came to campus and showed me a brochure with 20 or 30 different programs they were running of spacecraft to other planets and Earth observing satellites and things. And I said, I'll work on any of these, and which is the right thing to say, apparently, is that whatever that company is doing, if you want to work for them, say, I'll work on anything. That works a lot better than saying, well, I'll work on Mars stuff, but not any of this Earth observing stuff. No. Was there a repeater in there or something? I see the pizza's en route, so I may get interrupted here. Anyway, so it was a good time, because I had Voyager 1
I think we're losing you here, Mark. Let's see.
So,
Give it a minute. There we go.
yeah, somebody popped in there. So we got. So I said, well, the most I got taught in school was X band, and I said, don't worry, we'll tell you everything you need to know for working at 200 gigahertz. And they did. I got some good mentors from some of the brightest minds on the planet doing atmospheric research. So for my first 12 years, I was
Think we lost you. Let's see. There we go. Resume.
well. Well, I got you. let's see if I can share. Some pictures. So I ran. Am I still on? Yeah. So I recommend looking at these sunspots and picture of the rover there. Can you see the rover?
Yep.
Okay. And so here's a picture of that the helicopter took of the back shell. Can you see the back shell?
Yep.
And then at the bottom here is the shadow of the helicopter, which took the picture. Up here is a parachute, and this is a back shell, which apparently didn't land too softly. Anyway, so thought I'd get those pictures in before I lost connection again. So anyway, they hired me and back in '79, and I got to fly on the Kuiper Airborne Observatory. And not only did we do some experiments out the window to look at the atmosphere, which we were looking for chloromonoxide, which was part of the chlorofluorocarbons, which was a big issue in the 80s with the ozone hole. And this was before we even knew there was an ozone hole. And so we got to take a lot of data, and also got to the Kuiper Airborne Observatory was a C-141 cargo plane that had a 1 meter telescope on it. And so when we got up to like 40,000 feet, they would open the door to this evacuated chamber, and you could look at the stars with this telescope. And we were looking for molecular clouds that had diatomic molecules in them. We were looking for water vapor, which actually in Orion, they have a water vapor maser, which actually has amplified microwave energy beaming all over the place. So we were able to pick that up, and we got to take it down to New Zealand, where we got the closest approach to Halley's Comet. And so when I was on the Kuiper Airborne Observatory and I was on my tiptoes, I was the closest human being to Halley's Comet. And which was some important measurements, because at the time, the space shuttle was grounded because of earlier in the year when the Challenger accident happened. We lost a shuttle and it was grounded. So that was the only place where we could take experiments and take pictures of the comet without a lot of water vapor from the ground telescopes. So that was a lot of fun. And I brought my ham radio along. So I worked a lot of people as ZL0AAK in New Zealand. And then I went to Australia and got a license there. And I got WB6CIA. So I spent a week in Australia, visited the Deep Space Network, which had, 200-foot dishes to talk to spacecraft from all over the solar system, and also a lot of handheld 2-meter stuff in Australia. And then I went to Fiji, and I was licensed as 3D2MS and got to talk to people all over the world. I was getting pileups, and I say, QRZ, the G3, the G3 only, which is England, and Fiji is in the South Pacific. And I was still getting pileup because there was 3 guys from G3. So, I worked those individually, and that was a lot of fun. And then when I got back to JPL, worked on a couple of satellites that did mapping of the ozone layer. That way we could get map the ozone in altitude and globally, and for over several year period. So we got a 3-dimensional time-elapsed global map of the ozone layer. And we looked at chlorine monoxide, and we looked at water vapor, and we looked at oxygen and ozone, and we got the relative concentrations of those chemicals, so we could better understand the global chemistry that was going on in the upper atmosphere. The whole upper atmosphere, 200 miles of it, if you brought it down to sea level, would be the thickness of an eggshell. So that eggshell is what keeps us from the bombardment of high energy particles from the sun, as well as cosmic rays from the rest of the universe. So, it was considered important in those days to look at that stuff. And fortunately, from the data, we convinced enough politicians back in the 80s and 90s to do the Montreal Protocol, which eliminated the chlorofluorocarbons, and then which was destroying the ozone layer completely in the Antarctic in the winter, and was depleting it everywhere else on the planet. But because of these Kyoto protocols and the fact that we are creating more ozone, the ozone layer will probably get back to normal again in about 2040, 2050, somewhere in there. But we still have a lot of work to do to convince people about the effects of greenhouse gases. And despite all the evidence that there's just too much money in the fight for that. So that continues. But in the meantime, I'm just an engineer. And in the lab, I got to help a lot of grad students become PhDs, and some postdocs get to stick around. But the thing with having a PhD is you have to come up with your own funding source. Being an engineer, all you have to do is say yes whenever they ask you. Of course, you got to be handy enough to say yes. And I was privileged to work with some of the brightest minds on the planet, and they were like the only people on the planet that could do the jobs that they knew how to do. And so my job as an engineer was to, they'd scribble something down on a napkin, and for flight, I'd have to make a 100-page document describing what that piece of paper on a napkin was. Or if it was just in the lab, I'd just go ahead and build it for them, so that and sometimes even take the data, and then they would write the papers. So the PhDs would do all the proposals basically for free and write all the papers basically for free, and most of the money went to the hardware and me. So I was earning more money than the postdocs, and so I didn't want to go back to school and become a PhD and spend 10 years earning a lot less money than I was making. And I was a bachelor at the time. So so what I did instead is in my evenings, I would go into Hollywood, and I was building up a lot of automated music synthesizers to try and make electronic music for movies and television and playing rock bands and things like that, which nobody ever heard of. I worked in a played synthesizer for a band called Zombie Wolf, and we did Frank Zappa covers. You guys probably don't know who Frank Zappa is. Raise your hand if you do. But he was very big in the 60s, 70s, 80s, and 90s, and then he passed away in about 91 or so. Anyway, and also a band called Twist of Fate, where it was a gloom rock band, which was very popular in the 80s and early 90s. And I would build racks of synthesizer and sampling equipment for electronic music, all automated by a computer, which was a non-trivial task in the 70s and 80s and even 90s, because a lot of the protocols and MIDI was just coming out, and it wasn't quite set in stone. Computers were using Z80 processors and 6504s and S100 bus, where you had cards with 100 pins on them, but what was on the pins was slightly different between card to card. So some things it like the plus voltage, where some things like the grounded, and so you had to have jumpers to get all the protocols right for meeting the S100 standards. And some of the equipment had had their registers start with 1 and some of them start with 0. So when you did a program, you had to know which instrument you were talking to, because they were all different. So it was a very challenging time, but a time you can make your self a good living if you got around to it. But unfortunately, I got simultaneously married and on flight projects. So I got on the Cassini project, which was the biggest flight project there was in a spacecraft. I think it was the biggest spacecraft ever. It was the size of a bus, and that was going to Saturn. So it turned out to be a 20-year mission, and of course that was a full-time job, which would be 24 hours, 7 days a week practically if you let it. And being married, that's the same thing. That's also a full-time job, which can be 24 hours a day and 7 days a week, whether you want it or not. So I had lots of fun in the 90s, and being addicted to NASA flight projects, I didn't have time to do my music a lot. So, but all the experience I learned in building up racks of computer-controlled synthesizers, I used to build up 8 racks that was required to test the Cassini radio. And so these used Mac computers and PC computers and HP Rocky Mountain basic computers that were all tied together and remotely, and so that the software programs could do to automate all the testing for just the radio on Cassini standalone. We had to simulate a spacecraft with 6 different power supplies, and within the 8 racks. That was just the bottom half of one rack was the 6 supplies. Or was it 8? I think it was 8 supplies. And so, because we had 8 pieces of equipment, it was a redundant radio. So we had everything powered, and we simulated the flight computer to command and collect the data from everything. We had all the RF test equipment to simulate the radio signal going up to the radio, and simulate the deep space network collecting the data on the ground, and had to analyze all that data to make sure that the radio was working, and distribute that data to the rest of the project as required. And so we had our flight interfaces, and we also had direct access that only hooked up to our test equipment on the ground, and then just was capped off for when it was in space. So I got to go to Florida for 6 months while they assembled the Cassini spacecraft on the rocket. It was a Titan 4B rocket, and was launched in I think October 15th, 1997. My son was 8 months old at the time, so my wife and my son got to watch the launch from a little farther away. I was at the Mission Operations Center in Florida, and got to say the radios go for launch, and we looked at all the telemetry data up until launch, and then ran outside to look at the launch just a few miles away there at the Cape, and then run back in because it took several minutes for the telemetry to come back. So we had several minutes to go outside and watch the launch, and then come back in and watch all the telemetry come back. And so that was a lot of fun. Florida, Cocoa Beach is an interesting place to spend 6 months, and then came back to JPL. Worked on a whole bunch of other missions like the Mars Exploration Rover, Curiosity, Perseverance. I got to work on those. But at one point, also the Spitzer Space Telescope, I worked on a little bit of Odyssey. For Odyssey, when it was about 1 million miles away, they wanted to check the UHF radio. So you can't really use your handheld to try and talk to the Odyssey spacecraft from 1 million miles away. But we were able to go up to Stanford, where they have this very large dish of maybe 40 meters or so. And the whole blockhouse that housed all the equipment was underneath the dish, and the whole blockhouse rotated with the dish. And so we were able to get the UHF signal and slowly slew the spacecraft back and forth to figure out what orientation of the spacecraft had the strongest signals getting back to Earth, and the strongest signals being received by the spacecraft. This is to check the antenna alignment from 1 million miles away. Had to get into the far field to test the antenna there. And so we verified that the UHF was working well. I built up the radios and tested them and installed them for opportunity and curiosity and for Mars Science Laboratory. And at one point, Mars Science Laboratory got delayed by a couple of years because they didn't have all of the motors ready to go for launch. And we didn't, and I had Juno, which was a mission to Jupiter. And we had SWAT, which was, no, SMAP, which was a passive and active radiometer to measure surface water and moisture on land and the surface water on the sea. And so all three of those were ready for launch, but we didn't have a rocket for it. And so ran out of projects to work on. So they said, well, you're 55 years old, you're old, and you've been there for 32 years, you're old enough to retire. And we're running out of projects to put people on. So I ended up retiring from JPL, but I was 55. So thanks to some friends I worked with on Cassini and MER and Curiosity, I got some ins with some people at SpaceX. Got to talk to Elon Musk for an hour, and he was a very intent listener and asked a lot of questions, and on a very simple basis, and hired me. So I worked for SpaceX for 7 years. During the interview, he ran a video of a Falcon 9 first stage landing on Mars. And this was in 2011. And he said we would be landing on Mars by 2014. And so I said, well, you're going to need a radar altimeter for the landing. But, here it is, 2022, 11 years later, and we're still not anywhere close to landing on Mars at SpaceX. But they're working on it. And so let's see, any questions so far about my first 32 years at JPL or time at Cal Poly or anything like that?
I have a question.
Sure.
So compares, since you have both worked at JPL and SpaceX, how would you compare the working experience from both places? Working in both places, yeah.
Well, they're kind of the same and kind of different. JPL, there's a lot of paperwork involved that is extraneous from the actual doing the engineering work. As an engineer, you have to be very diligent about what you spend your money on and how you use your time, and because it's taxpayer money. When I was at SpaceX, if you needed a spectrum analyzer, you got a spectrum analyzer, and that's it. I mean, they didn't care if you got it from eBay or not, but you didn't have to have 10 people sign off before you would even consider it. JPL has a loan pool of test equipment, and so it's a lot easier to just walk over to loan pool and grab a spectrum analyzer. But if they don't have exactly what you want, then it takes a while to get it, and a lot of approvals and a lot of work on budgets. And
In fact, you could be spending more time on doing budgets than actually doing the work that you're trying to budget. I was on one project for Goddard, and Goddard says, well, we're kind of running short of money this year. What if we delayed the launch a year? Can you do a study to, as if we didn't have enough to do, but do a cost exercise on how much money we could save by delaying the launch a year? So we said, well, okay, we're going to give a unique account code for all the time spent on doing the budget exercise. And it turned out that when they looked at the cost of the budget exercise, that was as much as they wanted to save in the first place. So after that, they didn't give us any more budget exercises. But that was just one project. Every new project has a new manager who thinks he knows how to cut corners. And so when you get in that position, and they say, well, do we really need an engineering model, or do we need a prototype, or do we need to get so many spares and things like that? Can we do without those? The answer is yes, we can. Otherwise, they get somebody else to do it. But as an engineer, to be due diligent, you have to say, yes, we can, but here are the risks you're taking, and here's how we would mitigate those risks. And then, you tell them the likelihood of something going wrong, and you're going to need that spare, and then you don't have as much time to get it up and running, and so forth. And so you tell them how much more it could cost them if you take the risk of taking shortcuts. And so it's a manager's decision whether he wants to do the whole 9 yards, or try and save as much money as he can, because he doesn't get to have all the money he wants, or all the time he wants. And planets don't stand still for anybody. So you got to be ready, and the hardware has to be ready. And so sometimes you end up spending a lot more money just to make sure that if a problem occurs, that you're ready to solve it immediately instead of in the long run. So they make the decision, but then you're the one that's going to lose the weekends and the evenings trying to fix problems that are inevitably happen, but you weren't totally prepared for them. And you're in trouble if in a review they say, well, I think you should start as a baseline doing double shifts, which means somebody works from 7 to 4, and then another group works from 11 to or from 3 in the afternoon until 11 at night. And I said, well, if you start out with a project that in order to meet the deadline, you're going to have to do double shifts, what happens if you run into a problem and then you have to, go to triple shifts to try and solve the problem? Then you got serious problems. So you always want to, like, when you do your costs and budgets, you want to try and keep maybe about 20% margin in both, at least a month a year, and 20% of the cost. You figure out your budget. Well, if everything goes well, this is how long it's going to take, and this is how much money it's going to take, and these are the number of people you're going to need. And you present that to the management, and they say, well, we can't afford that. Can you cut 10% off everything? And you go, yes, we can, but
not recommended.
Then you hope that you make the right adjustments. Because what happens is then all of a sudden, oh my gosh, we're within a year of launch, or we're within 6 months of the launch, and then money's no object. They'll throw everything they got in order to make the launch date. So now people that you had working half time, which actually means they're working 30 to 40 hours on your job and 30 to 40 hours on some other job, which is always fun as an engineer to be working on several jobs half time. And they actually need somebody full time to do it. So they said, well, you should, we're going to budget you half time for 6 months to get this job. And it turns out, well, it really needs 2 people a year to do the job, but they give you 6 months half time. But there's a phrase in the movie industry called getting them pregnant on the project. So once they're committed, you know, and they run into a problem, then money's no object, and they'll do whatever it takes to get it done. But when you get to be my age, or you know, you got kids growing up and you want to spend time with them because they need you more, you know, you're less patient with management that tells you, well, we're going to have to make these cuts and see what you can do. But you know, when you're your age and you're young, you do what your boss tells you to do, and you know, hope you get lucky. Lots of times you do. Some of the bosses are really smart and say, yeah, no, we're not going to do that, and it turns out you didn't need to. So you know, that's why they get paid the big bucks. But you never know where a problem is going to come from. As an engineer, you say, well, these are all the problems you could have, which of course is never thanks to the mathematician Gödel, you're not going to completely specify all the problems. You just don't know all the unknown unknowns, but you list all the problems you got and your mitigation plan for each. And then, you know, when you make your budget and your costs and your schedule, then, you know, they understand what they're getting into, and you're not lefting, well, you said you were going to do it for this and it's not done. I said, well, no, I told you I would do it. You know, it would take 2 people a year to do this, but then we agreed on 6 months and half time. And then if you got that down in writing, then, you know, smart managers understand that and don't even ask you. But, you know, sometimes you get a manager that, you know, gets a lot of pressure on him, and so he puts that pressure on you. But, you know, so make sure you document enough stuff to, you know, cover yourself. And, you know, like when we first started out, you know, the Russians got Sputnik and everyone went crazy. Well, we actually had a spacecraft called Explorer 1 that was canceled because we wanted a civilian space program, Vanguard, to do it. But we had Jupiter rockets sitting in warehouses, and we had a Explorer 1 spacecraft sitting in a metal cabinet somewhere. And so when Sputnik was launched, I said, "Oh man, we gotta show them that we can do it." And so we had all this stuff, you know, off the shelf that we could then put together in like 40 days and get a launch off and look good, because, you know, we were prepared for what could go wrong. I mean, we had one copy of it and put it on the Vanguard rocket and it blew up. But then we had another copy in a storage cabinet that we could then just bolt on to Van Allen's original Geiger counter and strap it onto a Jupiter rocket, which Werner von Braun made. And we were able to launch that in just 40 days. And, didn't look so bad then.
Mm.
But, those are the things people have to learn the hard way. Fortunately, at JPL, most of the managers were once engineers, and so they know what's going on. At SpaceX, everybody was 20-something. I mean, the average engineer was like 26 years old, and I was 55 to 62. So somewhere there was like a couple of 4-year-olds working for SpaceX to compensate for my age and keep the average at 22 or 26. So it's kind of like a teenage sweatshop for a high-tech teenage sweatshop. Whereas JPL is, the difference between JPL and Jurassic Park is that one is a high-tech amusement park full of dinosaurs, and the other is a movie. So I'm one of the dinosaurs. And they call us graybeards for some reason. I don't know. So, but that's one of the good things about JPL is you have a lot of design reviews and you think, oh my gosh, I got a design review with the smartest people on the planet who are going to look over every decision I make and analyze my, my whole design and things like that. But they were once engineers in the same spot themselves, 20 years ago or 40 years ago or 4 days ago. So they're really there to help you. So you want to be as honest with you as you can and tell them all the issues and all the problems, and don't try and put anything under the rug, because they're there to help you. They're not there to burn you or to criticize you. They want you to succeed. So they actually want to be mentors, and they want to be helpful, and make sure that they feel like they're part of the, like it's their project too, and so it's partly their reputation. So they want you to succeed. So you can be honest with them, and they'll come up with the resources you need to help. And the sooner you tell them of any problems you run into, the sooner they can do that. I know I had one of my first bosses there at JPL. He was a chemist, but he knew a lot of electronics and a lot of computer programming, and was doing chemistry that only him and a couple other people on the planet even understood, let alone were capable of doing. But I was doing all the engineering for him, and he would come to me when he had a problem that he couldn't work out. And so, I felt honored to do that. So I would, listen to the problem, and then I would come up with a possible solution. And while he was telling me why my solution wouldn't work, you could see this light bulb going off in his head, and he'd come out with something totally from left field, or some imaginary field for a solution to the problem that he wouldn't have thought of if he didn't have that cueing by me, giving him a possible solution that wasn't going to be as good as his if it was going to work at all. But it took me to prod his mind with trying to explain why my solution wouldn't work, for him to come up with something even better that would work. So I got in the idea, I got used to giving my opinion whenever I'm at. In fact, if I go to a meeting, even now, and I'm the smartest guy in the room, I say, we're in big trouble now. Because I'm used to having a lot of smart people in the room, but if I'm the smartest guy in the room, then I try and give some bit of knowledge that will help all the other people in the room. And I may tell a story that is a non sequitur to the problem, but it gets people thinking about thinking out of the box for a solution. And that's important, even if it doesn't, say, oh, well, I got a problem that this resistor keeps burning out, and say, well, back in Galileo, we had this problem with chips that the memory chips kept popping off the boards. And it turned out that we had adhesives to put the chips down. And and we said, don't use any water with this adhesive because it made it expand and it would pop the chips off. But they were coming off anyway. And it turned out they were cleaning the parts with alcohol, and the alcohol had water in it.
Water.
The alcohol would evaporate, but it absorbed the water in the adhesive, and it would expand and pop the chips off. So, you guys will probably, hopefully, never have that problem. But remembering stories like that, helps you think of solutions to other problems, like those same memory chips on Galileo kept losing bits for no particular reason, and so they opened some of them up and they had water in them. So they had to open up all of the memory chips. In those days, there wasn't a lot in a memory chip. They were talking about, maybe 64 kilobits per chip or something. So they had a lot of chips on a lot of boards in order to have enough memory. And they had to drill a hole into each one, suck all the water out, and then glue the top off again. So after that, they said, make sure we have hermetically sealed chips in our spacecraft so that we don't get water inside the chip and start corroding and eroding some of the dyes in the chips. So these are the stories I hear in design reviews and in monthly management reviews. And, I try and pass them on, and I try not to repeat any of those mistakes. So it's always good to have somebody that can give you lessons learned on problems that can come up. How am I doing on time here, by the way? Are you guys bored with hearing me yet?
Nope, not at all. At least for me.
Okay.
Yeah, I think we can do another
For
10 to 20-ish minutes or so.
okay. Well, I got that much. So then I worked at SpaceX for 7 years, which when I started, I was like employee number 1,300. But then within a year, they went up to 7,000. But people didn't last
Cool.
very long. I mean, I lasted there 7 years. So when I started, I was employee number 1,300, and every mission we got a patch that had your employee number on it. Like your number 1, number 2, or number 1,300, or number 7,000. So when I started, my first patch was like 1,300, but my last patch 7 years later was 630. So half the people that were working there when I got hired left. Either they decided they wanted some other company that was a startup and that they would get on the ground floor and get better stock options, or they weren't good enough to cut the mustard, or they didn't like the fact that it was like a a fire drill all the time. And so they left. And I left because we had a communication system that when I got there was having like 200 issues a year that you had to write up. This was a problem. This is how we need to solve it. And this is how we solved it for this mission. This is how we'll prevent it from happening again on the next mission. 200 of those a year, every year. But and then one year it was like maybe half a dozen a year. So, I pretty much solved all the problems. So they decided they didn't need me so much anymore. And I ended up working at JPL again. I would have got hired sooner, but this was 2019, and Donald Trump decided that he'd rather have a wall than a government. So I got delayed like 6 months before I was actually hired, but and hired as a contractor. So I'm actually working for another company, whereas at JPL you're normally a Caltech employee, but Caltech hires contractor companies to fill the gap, and when they don't need them anymore, then they don't. They just say, "Well, sorry, we don't need this employee anymore." Whereas if they're a Caltech employee, they try and find other work for them to do. Anyway, that was 3 years ago, and since I started working there, I worked on Mars 2020 ADLO, which is the assembly, test, and launch operations, where they put together the rover, and we tested everything out to make sure everything worked on the rover. Then I worked on surface water mapping mission. I worked on NISAR, which is a joint radar mission with India. And right now, there's a bunch of people in India trying to get that thing finally going, which is a real fun time to be in India right now. And let's see, then I worked for Psyche, which is a spacecraft going to a heavy metal asteroid that could be worth hundreds of trillions of dollars worth of minerals on it. So it's going to orbit that and figure out, the composition of heavy metal asteroids. So that this week is going to the Cape Canaveral and will be launched in like 6 months or so. And I'm working Perseverance operations. So I have to look at report how the telemetry is coming back. I work on the telecom system. So Perseverance is on the ground on Mars, and we're on the ground on Earth. So we have to, I have to determine the health of the spacecraft or the rover. And we have an X-band signal that goes directly to Earth and to the Deep Space Network. So I have to report on the status of the Deep Space Network, which is in Goldstone, California, out in the desert by Barstow, Canberra, Australia, which is near Madrid's, which is near Canberra, Australia. It's actually Tidbinbilla, and Madrid, Spain. And so they all have very large dishes, 70 meter and 35 meter dishes to talk to Mars with via X-band. So we have a high gain antenna that points to Earth, and a low gain antenna that just sits there and basically does beeps and picks up the carrier from the ground to lock onto the signal. But we also have a UHF radio, and we have 4 orbiters. We have the Mars Science Laboratory. No, I'm sorry, Mars Reconnaissance Orbiter. We have Odyssey. We have TGO, and we have Maven, and they're orbiting around. And so when they get above the horizon, we send UHF data back and forth with that. They collect the data on the orbiter and then use X-band to send it back to Earth. So I have to know what the status is of the 4 orbiters, as well as the rover, as well as the Deep Space Network. And then how the data actually gets from the Deep Space Network back to JPL and onto people's screens is somebody else's job. But, you know, when they don't get data on the screen, the first thing they say is, what's wrong with the radio? And so, you know, saying, well, gee, it worked yesterday isn't quite good enough. You have to actually check the status of all this equipment, the rovers, the orbiters, the Deep Space Network. You know, are there any solar flares that could affect things? Weather at the ground stations, all this kind of stuff you have to know about so that you can report to the project, you know, hey, everything's healthy. You know, they probably just having some data issues at a computer. So, you know, most everybody on these projects looks at the radio as just the part of the wireless link between the flight computer on the spacecraft and their computer on the ground. But all the telecom people think that the spacecraft is actually a radio with a bunch of peripherals added onto it. So we feel it's the most important part of the radio is the radio, because without a radio, everything else could be working perfectly, but you'd never know it. So if there's something wrong with any part of the spacecraft, you need the radio to find out what's wrong and to have the ground send commands up to fix it. So that's the important things. So now I'm getting close to retirement age, and fortunately those sunspots are going up. So I want to get a place on a hill, perhaps by San Luis Obispo, and start growing an antenna farm, and see if I can get DXCC 5-band worked all DXCC and worked all states, and do some moon bounce and other things like that once I retire. Who knows, maybe even play some music. So, but I can't tell you that much about SpaceX because it's proprietary and we have restrictions of ITAR and which is saying that we can't transfer technology. You know, I don't know if you're all US citizens or not. So I can't tell you too much about the technology that we're using on any of this stuff. But it has evolved over the years. I started in vacuum tube radios, and now everything is, you just program it in an FPGA and hook it up to an antenna, and that's how everything runs. So I guess the last things I can depart to you is enjoy your time at Cal Poly or wherever you go to school. There'll be the rest of your life won't be anything like this, thank goodness. But so enjoy it. Don't be afraid to fail. Take the hardest classes you can. Study till you puke, and then you know, get back on the horse and get back on that Bronco and study some more, and because it will be worth it. I took a whole bunch of graduate courses while I was an undergraduate because they only offer them once every 2 years, and So I wasn't going to wait 2 years after I graduate to take those courses. So I took them while I was a senior. I was taking like 27 units in a quarter, but it was worth it because that probably helped me get a job at JPL. I did get 50 rejections from other companies. So, but I got 4 offers from JPL. So I guess I got lucky there. And but timing was everything, you know. We're applying to say, yeah, I can start right away, right when everybody else was working on Voyager was a great opportunity for me. And been there ever since. Just say yes to everything, and you end up working on a lot of projects. So, I guess my final word to you before I open it up for questions is everything you know is wrong. So, any questions?
What was the turnover like for young people in SpaceX? I mean, and has that changed, or is that not been same?
What was what like at SpaceX?
The turnover for young, kind of new career
Yeah.
employees.
Well, turnover. Well, it's like the average was maybe 3 or 4 years for engineers. Every Friday there was at least we had like a floor of 300 engineers just working on the avionics or the electronics, and every Friday we all stood up and applaud the 1 or 2 people who were leaving that week. So you know, it goes up and down, but yeah, even the higher up management was had you know, some people were there year after year, but some of them were there for a few years and then gone. But they all eventually leave. That they have a stock option that you're fully vested after 5 years. So I made it to 7, and that was pretty rare. A lot of when I left, there was of the 30 or so telecom engineers, there was maybe 1 or 2 that were there before I was. All the rest were hired after me, and a lot of them left, and that was, you know, 2 or 3 generations of telecom engineers. So yeah, I wouldn't buy a house to live in and work at SpaceX. I stayed in South Pasadena and drove the 25 miles to to SpaceX and back. It was only like 4 miles to JPL, but it was 25 to SpaceX. Got in 4 accidents my first 4 years there, driving the freeway, bumper to bumper. But yeah, I mean, you might want to buy a house for an investment, but don't expect to be spending your whole career at SpaceX. Whereas JPL, people who were there when I started back in 1979, some of them are still there and never left. And, you know, they even took me back. So, but wherever you go, you'd be surprised how well you do when you by, you know, making friends and making a lot of contacts. And because there's a lot of people like at Cal Poly at JPL and some at SpaceX too. And some of them, I knew a Cal Poly SLO graduate at SpaceX, and then I knew him, and then he quit before I did, but he went to JPL, and so I saw him when he was at JPL. So it's kind of a small group of people we got here with, especially with hands, and you can use them your whole life. And so keep in contact with each other, because you never know when. I mean, you need help on a homework assignment now. They may give you a job 20 years from now, or vice versa. So yeah, stick together, guys. Over.
All right.
Any other
Anyone
questions?
have? Yeah.
I have a question. I don't know how much you can tell us about the link budget. Like, what's the margin on the received signals from space, and what's the received hardware look like?
Well, you try and keep at least a 3 dB margin. It's not always possible, but you know, if you have to add another antenna because of a particular orientation during a trajectory correction maneuver or something like that, you know, keep that 3 dB whenever you can, just as a rule of thumb. And when I used to work for Edison, and when I was doing the microwave links between substations for Southern California Edison Electric Company, all our substations have a microwave link that go to Alhambra or other substations, so that you can remote control their operations, especially if the landlines go out or something like that. So they tried to be 99.99% reliable, which is something like a half an hour a year, but never turns out to be that way. It's usually like you lose it for half a day once a decade or something like that. So that's our typical margins that you want to keep. Over.
Thanks.
I got a question. How did you make sure that RF connectors didn't come undone millions of miles away?
Well, connectors are probably the biggest source of failure, period. On the ground, in space, whatever, especially if they get used. So you always, inspect them to make sure they're clean, and clean them if you have to. And then you use a torque wrench to make sure that you have the right amount of pressure on the connector. And then they have special staking compound that will that you put over the connector mating surfaces in certain spots, that helps them from rotating on their own, or it also will tell you if they have rotated on their own because the staking compound is broken. Another thing they do is some connector types have holes drilled in the connector outer sections, where you can have safety wire, and you tie the safety wire through all the connections so that they can't rotate, because the safety wire kind of locks them in position. Many connectors have a locking function that, when you've got it completely mated, there's a detent that has to be overcome for them to come loose. Also, keeping them from being pulled out, you have strain reliefs, so that the body of the connector is usually clamped to the braiding, and then you have insulating either from heat shrink or from a tape that expands and self-fusing tape to make sure it's weatherproof, and also adds a reinforced strength where the connectors meet the cable. They prefer crimping to soldering because it's more repeatable, and you don't have too much heat causing melting or not enough heat causing cold solder joints. But crimping, you have a tool that actually won't make you over crimp, but will add just enough tension to hold the wires together. So does that answer the question? Over.
Yeah, that does. Thank you very much.
Any other questions? Okay, well, thank you all for staying awake, at least the ones I can see. And I hope you all graduate and have good fortune. And who knows, maybe one of you will actually be on the first mission or a future mission to Mars with people on it. If not, there's plenty of good projects in industry and in academia and at NASA and NASA's competitors. Thanks.
All right. Yeah. Thanks so much for presenting. And to anyone watching this on YouTube, yeah, feel free to contact the club after watching.